Hello, in this video, we're going to discuss application of the gas laws, specifically PV equals nRT and 22.4 liters per mole to gas stoichiometry. So we are going back to stoichiometry, and not to scare you, but just remember that stoichiometry just involves finding some way to find the moles of a compound and then using that in the balanced chemical equation to find the moles of another compound. And around that moles to moles, we're going to layer other things. But there's this little twist that can make life very easy for you if you recognize it. In the first problem we're going to look at, we're going to assume, actually, we're going to be told that the wanted and given are both gases. And these gases are at the same temperature and the same pressure. When that happens, according to Avogadro's principle, the coefficients in the balanced chemical equation can then also represent the volume. And this is because, according to Avogadro's principle, the volume is directly proportional to N. So if we know the volume and everything's at the same temperature and pressure, the volume and the number of moles are essentially the same ratio. Now, you can see this by looking at the equation I have down here, where we have a nitrogen gas and 3 hydrogen gas forming 2 ammonia gases. And so the coefficients out front can represent moles. So we have 1 mole and 3 moles and 2 moles. Now they could also represent molecules. 1 molecule, 3 molecules, and 2 molecules. But because of the way Avogadro's principle works, at the same temperature and pressure. So if we are at, and this only happens at the same temperature and pressure, that we can put any volume unit, 1 liter, 3 liters, and 2 liters, or 1 milliliter, 3 milliliters, or 2 milliliters, sticking with SI units. We could also use gallons or pints, as the old English chemists used to use, but we're going to stick with milliliters. So be on the lookout for specific problems that have this in them. So for example, if I give you the following problem based on this reaction, how many liters of nitrogen gas and 100 degrees Celsius and 1.4 atmospheres can be made starting from that 6.3 liters, also at 100 degrees Celsius and 1.4 atmospheres. So this is going to be our given, and this is going to be our wanted. And as long as the wanted and given are at the same temperature and pressure, then we can just use that the liters that we just discussed up above as our ratio. Makes it really nice and easy. Now be careful. Do not use 22.4 liters per mole here, because it's not at STP. You might get the right answer at the end, but if I see you using 22.4 when we're not, liters per mole, we're not at STP, you will lose points. So the liters of nitrogen gas, we're going to start off with our 6.3 liters of hydrogen gas. And now our ratio, instead of being mole to mole, we want liters of nitrogen, liters of ammonia. So go up to the 2 up here, 2 liters of ammonia. And we have hydrogen, so let's go to the 3 liters of hydrogen here. And now we're really pretty straightforward. Liters of hydrogen cancel off. 6.3 divided by 3 is 2.1 times 2 is 4.2 liters of ammonia. Okay, so liters of ammonia, when we have the same temperature and pressure, are pretty easy to get to. Now, the next kind of calculation is going to be, suppose you don't have gases at the same temperature and pressure, or even worse, you don't have a gas at all, but you've got a solid that's going to give you a mass or something along those lines. So you've got two options. If we're at STP, then you can use 22.4 liters per mole as a conversion factor between the number of moles of the gas and the volume of the gas. Otherwise, you can use P and T, the given pressure and temperature, in PV equals nRT to convert between the number of moles and the volume. And then in this case, you're going to have to use dimensional analysis. And yes, you are going to have to pay some attention to the units of the given and the wanted. So in A here, this is a balanced chemical equation. I want to know how many liters of CO2. So here's my CO2 gas at STP. STP means I can use 22.4 liters per mole. So remember that STP is 22.4 liters per mole, can be produced from 25 grams of ethanol. And notice that ethanol is a liquid, so you cannot assume anything about gases with ethanol. So let's start off with our 25.0 grams of ethanol. Now, remember, we want to do the following. Let's think about a roadmap. We have grams of ethanol. For stoichiometry, we always want to get to moles first. Then for moles of the ethanol, we can get to moles of our wanted. And then we can use STP, we can use 22.4 to get to liters. So let's see how that works. First, from grams to moles is just like we've done for, I don't know, since October when we did moles. Grams to moles is the molar mass. So I'll spot you the molar mass. 1 mole of ethanol is 46.08 grams of ethanol. And so the grams of ethanol cancel out. Now we have our moles of ethanol. We go to our balanced chemical equation where we have, let me change colors so you can see what I'm doing here. We have 2 moles of our CO2 for every 1 mole, implied 1 in there, of the ethanol. And now the moles of the ethanol cancel out. And now we can finish off. We've got moles of CO2. CO2 is a gas. So now we can go to our 22.4 liters per mole. 22.4 liters of CO2 and 1 mole of CO2. The moles of the CO2 cancel out, leaving us with liters of carbon dioxide, which is what we're looking for. And let's see, we can go through the calculation. If you're going to stop along the way, just so you can check yourself out here, this gives us 0.5425 moles of ethanol. And this will give us 1.085 moles of CO2. And then we take that, multiply by 22.4, and round to the right number of sig figs. We have 24.3 liters of CO2. All right, so not so different from other stoichiometry calculations. By the way, this will be on the test, so this is where we're going to get some stoichiometry calculations in our tests. In B, and I don't know why I've got that extra 2 in there. In B, now we're going to turn this into a slightly more complicated problem, because notice I'm at 112 kilopascals and 38 degrees C in this reaction. So now I can't assume 22.4 liters per mole. It's not STP. So what do I want? What can I do here? If I want to know how many grams of hexane is right here, C6H14, can be burned by reacting with 25 liters of oxygen gas at that pressure. So I need to know that I need to go from, let's do a little roadmap. I need to go from liters of the oxygen to the moles of the oxygen, then moles of oxygen to moles of the hexane, and then from moles of hexane to grams of hexane. So to go from liters to moles, I'm going to use my favorite equation now, that PV equals nRT, rearrange that to find that N, the number of moles, which is what I'm looking for, N is equal to PV over RT. One thing I do have to do, my temperature, don't forget, this is a gas law, so I need to have my temperature in Kelvin, so 38 degrees C plus 273 is going to give me 311 Kelvin. Okay, so show me that calculation. And now I can calculate the N, the pressure, 112 kilopascals, times the volume was 25.0 liters. R, because I've got kilopascals, I need my 8.314 kPa times liters over moles times Kelvin, and multiply by 311 Kelvin. And I'm not going to cross off the units for you there, but the units will cancel out and leave you with moles, and that will give us 1.083 moles of oxygen gas. All right, now that I've got the moles of oxygen gas, I am able to get up into my stoichiometry. So now I've got the moles. I'm going to start here, and I've got this last part of the stoichiometry to go. I have 1.083 moles of oxygen gas. Let's go to our balanced chemical equation, where I have 2 moles of C6H14 in every 13 moles. Some nice coefficients there, huh? Moles of oxygen gas. And cancel out the moles of the oxygen gas. Now we have moles of the hexane. So moles of the hexane to grams of the hexane. As before, molar mass. I'll spot you the molar mass of the hexane, 86.2 grams of C6H14 for every 1 mole of C6H14. And that cancels out there. And if I were to stop and just give you the moles of the hexane, it would be 0.1666 moles of the hexane. So in case you want to follow along there. And then multiply that by the molar mass of hexane, and that's going to get us 14.4 grams of hexane. Oopsie, C6H14 needed to burn that much or react with that much oxygen. If you are going the other way, if you're given the grams, like it's going to give you the grams of the hexane and go the other way, you'd start off with the grams and then go to moles. Then you'd calculate the moles. So this is moles of your given to moles of the wanted. And then the moles of the wanted, you plug into PV equals nRT to solve for V, rearranging V is equal to nRT divided by P. And we'll get the volume in liters, just like we wanted to. And there will be a homework problem or two using that as well. All right, this is stoichiometry using gases. Hopefully everything is going well for you. The homework is accompanying this, and I will see you next time in class.